Hello you guys. Well, today we're going to talk about with this new topic, which is functions. We have seen before the Cartesian plane and how to work with it using coordinates and locating different spots or points um, into the four quadrants of the Cartesian plane. We also have seen that we have an x-axis, which is the horizontal one, and we have a vertical axis, which is the vertical one. And it goes from negatives to positives depending on the quadrant that you're working with. So, with that information, we know that what would we need that for? All right, we would need that for get a solution of different, in this case, equations, which in this part we're going to see as functions. All right, and we're going to see also what domain is and what the range is as well. So for every function, we should have a relation. So we're going to see function versus relations. And we see the small drawing here in which we have a relationship, but well, not everything is a relationship. We have relations everywhere. Could we have a school without teachers? Could we have chocolate cake without chocolate? No, right? So that's exactly what a relation is. A relation is just a relationship between sets of information. A function is a well-behaved relation that is giving a starting point. We know exactly where to go. So here is an example. People and their heights. All right, what is your height, you guys? So everybody has a height, and everybody is an individual, right? So there is a relation between you and your heights. So as example, the pairing of names with the heights. So let's say that student A, his height is 5'7", and student B, his height is 3'4", etc. So we can think of this relation as an order pair. Height and the name, or name and the height, whichever could be. But there should be a relation between both of them. So let's say that Joe, who is student number 1, is 6 foot, and Mike, who's student number 2, is 5'9", but to locate it like in a better place in the Cartesian plane, we're just going to convert it in 5.75. Then Rose is student number 3. She measures 5 feet. Then Kiki, student number 4, 5 feet again. And Jim, student number 5, is 5 feet 6 inches, which for related to better related into the Cartesian plane is 6.15. So continuing with that, we can have here a Cartesian plane actually, and we are going to name our Cartesian plane in both ways. Alright, it doesn't matter how you want to do it. Actually, at this point, you can call the x-axis height like here, and also the y-axis with the names of the students, or you can do it backwards. You can put the height into the y-axis and put the in the x-axis we're going to name the students. All right, but in the same way we have to locate the spots, the points. So both graphs are relations. We wouldn't have these students with these heights. So James is 6'5", Kiki is 5, Rose is 5, etc. Right? Or backwards. So the height and the name is not well behaved, the way we can see it here. All right, it makes such as, let me put it this way. All right, it makes something like this. And given the height, there might be several names corresponding to that height. So how do you know then where to go? For a relation to be a function, there must be exactly one y value that corresponds to a given x value. We could never ever have two x values in two similar x values. We will never have them. So in this case, we have two 5s, all right, and they are located in x. So this shouldn't be possible. So this means that this is wrong, right? But in this case, what happens? All right, we have different x values because they're all different people, and we can have the same values in y, but since they're with different people, this should give us a function. So this is conclusion and the definition. Not every relation is a function, but every function is a relation. So the definition might be: let x and y be two non-empty sets. A function from x into y is a relation that associates with each element of x exactly one element of y. So recalling a little bit from what we've seen before, the graph of height name, what happens to the height in 5? Well, it repeats, okay? It repeats right here. So we're going to make a vertical line test. A set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. So once, and I'm sorry for this mistake, we have decided on the representation of a function, we ask the following questions. What are the possible x values? Names of the people from our example, and y values their corresponding heights. For our function, we can have. Alright, so this should be correct because every name of a person is different. So we are never going to repeat x, even when we repeat the values in y, right? So with our example, the pairing of names and heights, x equals a name and y equals a height. We can have many names for our x value, but what about heights? We can have many heights. We can have a lot of same values for y as long as they don't repeat in x. Okay, for our y values, we should not have 0 feet or 11 feet since both are impossible. Alright, well, in this case, we know by common sense that nobody measures 0 feet and nobody measures 11 feet, alright? So that way we know that there should be a limit in the heights of these students. So thus, our collection of heights will be greater than 0 and less than 11. We should give a name to the collection of possible x values. Names in our example. Remember that in x we had all of the names of the students. And to the collection of their corresponding y values. Each student had a different height. Everything must have a name. That's their relation. We cannot have a relation if we don't have two different pieces of information. So the variable x is called the independent variable, and the variable y is called the dependent variable. Why? Because y reflects what x is evaluated with. Alright, we're going to see that as well. For convenience, we use f of x instead of y. So we use the function of x, which equals y, the value that we're going to get for y. So the ordered pair in new notation becomes x comma y equals to x comma f of x. F of x is the result of the equation that we're going to make with that function. So with this drawing, we are representing that f of x, which is the vertical axis, should have a result. So in order to locate a coordinate into the Cartesian plane, we should have a value for x and the resulting value for y, which is the result of the function for x. So what is our domain and our range? Suppose we're given a function from x into y. Recall for each element x in x, there is exactly one corresponding element y. Alright, for every x there should be a y, which is the function. This element y equals the function of x in y we call the image of x, or the range, however you want to call it. The domain of a function is the set of x that is a collection of all possible x values. The range of a function is the set of all images as x varies throughout the domain. Alright, the domain is all of the values that we have for x, and the range is all of the values that we get out of my domain. So every student has a height, every student is the domain of all students, and the range are the different heights that they have. So this is our example. In our domain we have Joe, Mike, Rose, Kiki, and Jean, which is the set of x's, and their corresponding y's or ranges: 6, 5.75, 5, and 6.5. 5 we are only having it once because two of our students measured 5, but we don't repeat them in the range because it's the same value. So we have more examples here. Consider the following relation: f of x equals the square root of x. Is this a function? What is the domain and the range? Alright, so this is our representation of what it is. So we're going to set the domain. The domain moves along, as you can see here, through x, and it goes way to the right. Alright, with the values that we are calculating for x, we consider 1, 2, 3, 4, 5, etc. So then we evaluate those into this function, into square root of x. So we get the square root of 1, the square root of 2, etc. And that is going to give us the points that we're going to plot in our Cartesian plane that would follow this very line, as you can see right here in the green part, and they move along the x. Alright, and it stops right here when we get to 5 in the domain. But what happens in the range? Alright, the range is all of the values that we're getting out of the same function, but these are the resulting points that we get while calculating it. So it stops in 2.2, let's say. Alright, and as you can see in this image, it moves along the vertical axis, which is the y. That's the range. Alright, so in this case, once drawn the function, we can say that the domain equals from 0 to infinite, because it could go way beyond this. It could not stop. If you give more values, it will not stop.